understanding what we're doing. The first part is the 6.3, proportions. Most importantly, why we do a confidence interval. We don't know enough about our population, so we use our sample to make an inference about your population. Again, in this part, I had a population proportion, the part over the whole, x over the n, for my population. For my sample, I do the same proportion, only I call it a p-hat. So my p-hat is still x over n. It's the same proportion. Only thing is, it deals with your sample, not your population. We make an inference about our population based on our sample. When we get to your standard deviation, first we look at your variance, that has the square for your population. We're looking at an S squared for your sample. Standard deviation is the square root of that. Standard deviation is the 0.x for your sample. Let me do something. Okay. So, yes. It's not letting me.
How does that happen? It wasn't even.
Rachel, got it?
Yeah.
Guys, that wasn't the cue to start talking. No, I didn't. So in a survey of 1,023 adults, this is your sample, obviously. There's a lot more people that work a night shift at some point in their lives. This is your sample. It's done from a survey. 552 said some point in their lives they worked a night shift. Find your p-hat. That's your proportion from your sample. Your q-hat is 1 minus p-hat. The reason they call it a p-hat is because the proportion p is from your population. So we have to have a way to differentiate. So to keep the p and the q kind of consistent with your binomial, they do a p-hat and a q-hat. And all they asked for these two was to find your p-hat and your q-hat. Everybody okay with this part? Okay. Then we built a confidence interval for exercise 25.
Are you going to give us the formula?
I'm going to give you all formulas. You don't have to memorize any formulas. But I will not help you with the calculator steps. If you want to use the calculator, that's up to you. That's on you.
Oh, usually those formulas have on the final result.
And the final you get into. I give you all formulas. I don't expect you to memorize it. That's like such short-term memory. You memorize, and as soon as you go on to the next formula, the other one's
My last class, like my last math I took, they tried to make me memorize all these formulas.
Some of the formulas you continually use,
Crazy.
but these you don't use again. These you don't use again. Okay, let's build a confidence interval. Your confidence interval is the same as we've been doing. And in this case, our point estimate regression. Instead of x bar being our point estimate, your p-hat is your point estimate. It's an estimate we make for the population based on your sample. So we're using a p-hat plus or minus the margin of error. Here's your margin of error formula. It uses the ZC, so a z-score for your confidence interval. Our confidence interval is 90. Remember, we do an inverse norm. Minus 90 divided by 2. That'll give you your ZC. You get your ZC at 1.645. And if you look at table 4 for the z-scores, there's a little table on the bottom of it, and that'll help you out for your more popular ones. Plug in your p-hat, your q. Your q-hat over n. Make sure this stays underneath the radical. Put it in exactly the way you read it in your calc. 1.645 square root, and just put it in like this. 0.51 times 46. Keep this all under the square root. You don't need anything extra extra in there.
You just do the stat test.
You can do the stat test. We'll get to that in a second.
It's the one property Z.
One proportion Z interval. Okay, so then you build your proportion interval. Rachel, let's go with you. Mariah?
Yeah.
Good. You build your proportion interval. Now, if you want to use your calculator, it is in your calculator. Go to stat, go to test. It is past the intervals. Pull up the intervals. Make that interval be at the top because you're only looking at intervals. One proportion Z interval.
Yeah. This more? Can I?
Excuse me, can I have her
Yeah.
back for 1 second?
Yeah. As long as you return it. Okay. X and N. Guys, see the X in the end? Go back to your original one. Enter 552. Oops. 552. Enter 1023.
No.
Hold up, wait a
Oh
minute.
my gosh.
Oh,
How much makes it? What?
We're getting a record.
and so I'm on a delay here. Okay, and calculate. Now, if you want to go backwards and find your margin of error, take the highest proportion and subtract your p-hat. Look, they give you your p-hat. So take the highest one and subtract your p-hat.
And then what you get?
Margin of error. You'll get your margin of error. Okay? So if you don't want to use your formula,
When you built the margin error, then what did you subtract or minus?
the p-hat. We built your interval from your p-hat. Remember before we used to use your x-bar? This time our point estimate is our p-hat. It's your p-hat. Okay. Everybody good with this? Good? Alright. Makes sense? And don't forget, your decimals are small, but they make more sense looking at a percentage. If I want to use this interval, and it looks like this, I'm making an assumption based on my sample for my population. So this is my population proportion. I want to be 90% confident that my population proportion for the adults that work night shifts will be between 51% and 57%. It sounds better when you use a percentage, when you make your interpretation, because 0.51, 0.57, it doesn't really sound a lot to us. So if you want to use a percentage in your explanation, that's a little bit better. A confidence interval for 26. So you found your p-hat and your q-hat was based on 800. There were 90 people. X was n. X was 90 out of 100. So we built our margin of error. You want a 98%. There's your ZC for 98. P-hat plus or minus your margin of error. You can do it again in your stat test. You prefer that. You got to be able to show me your calculator step and how you found your margin of error if you use a calculator. Everybody understanding that part?
Yeah.
This one will take you all the way through. This is finding your sample size. And how do we recognize this? Because it says find the minimal sample size needed. This one says no preliminary estimates are available. So we said there would be two things. If there's no preliminaries, you got to be middle of the road. 50%, 50%. Next time I'm sending you out, guys. 50%, 50%. 0.5, 0.5. So you plug in your 0.5. I'm going to give you this formula. You need to be able to look for your 95% confidence, and who must be accurate within. There's your margin of error. However, you have to make this be a decimal. Don't give me 5, because it's going to change your answer. So we're going to just plug this in. Rule of thumb, always round up on your end. You can't have a partial person to respond. Always round up.
Don't set it up when you're asking me to do that.
Or 5. It's like 50%, middle of the road. I think 50% will say yes, 50% will say no. Then they usually redo it and they say we found preliminary from a previous study, and they went with the 0.63, 0.37. You should see that you need less in your sample. You're a little bit more exact when you have a preliminary. Now, if your preliminary and your actual are close, you're not going to see a big difference. The 50 is like 50% gives you the highest you're going to get. And then you can see them change from there. Okay? Can everybody do this? This is the only one that gets a sample size. The chi-square does not get a sample size. So now we're going into chi-square. Okay. And the same thing on your test. I'll do all your proportions, and then I'll ask you for a critical value. Now you're in chi-square mode. So chi-square will say, find me a chi-square value when n is 25. You're going to use your table 6. There's no calculator step. You notice your table 6 says degrees of freedom. I'll give you a table 20. I'll give you a table 6. You look up your degrees of freedom. You do it the same way you do your inverse norm. 1 minus 0.98 divided by 2, but do not put this in inverse norm. It's going to give you this. You're going to subtract it from 1, and you're going to look up these two values. Don't get hung up on who's right and who's left. The left is lower. So in the formula, you got to put the right on the left side. So don't get hung up on who's right and who's left. Make a chart like this. These go from 0 to infinity. Remember, they're skewed. They're not normal.
Do you have to give me a graph?
No? But if you need to figure out what's left, what's right, the graph is helpful. Yes.
So we just use the table. So first we do like the like what we do for confidence level, then use up with the table for like decimal points, and the tables
And if you notice, your table where it has that alpha in here, and it goes like this, if you draw a line here, these are symmetrical. So then a 0.95 uses a 0.05. They add up to 1. Okay? Okay, this one too? Yes.
Don't ask, sister.
Just look at one.
Oh, no, no.
And then sign the smaller one or the left.
I'll do pass around the same thing.
You're in high square, you go to your area to the right, not area
Pass
to the
around the
left.
table.
Okay, guys, Nick had a good point. Nick assumed the smaller one was the left one, but remember, chi-square works the opposite. It's the area to the right, not the area to the left. It doesn't work like your Z. So I said, don't get hung up over that. Just pull out your two numbers. Then the smaller one, assign to the left. The larger one, assign to your right.
X2 or X2 doesn't really matter. The lower one always goes first.
The lower one is the left.
Or when you do the integral,
When you do your equation, the right one goes on the left-hand side. Because you need to divide by a larger number to get a smaller number. Okay, so that's why, don't get hung up. This is the only one that the area counts to the right, not the left. So don't get hung up on that. Just find the two values. The lesser one is the L. Okay? Put this in your calculator. You are looking for your SX. Your sample. This is a sample. So you are looking for your sample standard deviation.
Wow.
Could you use this as 7 for that one? 7.0?
You could do 7. You could do 7.
I'm rounded.
I go out. Okay, this is my deal. I go out like 3 decimals. So this way, if you round it to 1, you can see where it is. If you round it to 2, you can see where it is. As long as I see where your rounding is, I'm okay with it. So I tend to round a little extra, so that if anybody goes a little less, they'll see where the rounding is. And I'm fine with whatever you show me. Rule of thumb, we used to do the mean 1 more decimal, and the standard deviation 1 more decimal. So it's nice to go at least 1 decimal. Obviously in this one, it would just be 7. So that's fine. So I went to 7.002, so that you could see where you're rounding anywhere in between there at 12. You have to use a formula. There's no calculator stuff. N minus 1 is your degrees of freedom. If you're finding the standard deviation, and you put it in here, you have to square it to get to the variance. So make sure you square it. Then when you're done, take the square root of the whole line. That gives you your standard deviation. When you find your variance, then you find your standard deviation. So we can be 95% confident that the population standard deviation for super zoom digital cameras will be between 5.215 and 10.656 of ounces. Okay? Very right. That's less than a pound.
Where do you put the
Oh.
16? Where you got a little, where does the 17 degrees of freedom? Or the 17 is the N and the degrees of freedom is 16.
16.
And then you plug that into the N minus 1.
You can plug in 17 minus 1 or just plug in 16.
Okay. And then minus 6 times SX.
That's the standard deviation, then we have to square it. Then we take the larger of those two values and put it on the left-hand side because we want this to become a smaller number.
Larger of two values.
The two critical values that you found in the one before this, or you have to find this 1 minus 0.95 divided by 2. You find those two values, they gotta go in here.
Okay.
The larger one goes on the left because when you divide by a larger number, you get a smaller number. You want this guy to look like this. You want it to be in order. Are we good?
Wait, that's the answer's not true.
No. I was giving her an example of how you divide. That wasn't the answer. And the last one, can everyone put this in their calculator and find the standard deviation for the sample? Not the population. So how many population ones am I going to get tomorrow? None. Good.
So none.
We're going to find the sample standard deviation, which is your SX for samples.
And the population is over.
Oh, you're going to find your two critical values. You're going to plug them in your formula. And then you're going to tell me you're 99%, you're 98% confident that your population standard deviation for acceleration times is between 0.89 and 1.75 seconds. 1 second.